Today's topic is impulse and doing example problems or doing problems with the idea of impulse, which a lot of times is overlooked. People try to do their SUVAT equations, their motion equations, or they go to F equals ma. And impulse a lot of times is an easy way to do it in one step rather than having to calculate things like accelerations. It'll get you to the same spot that the other things would. It's not like you have to pick one method that's always going to be right. That's kind of the beauty of physics, is they all give you the same answers. But this is just an overlooked method of doing things that I think if you kind of have this in the back of your head and you'll have the formula for impulse, that it sometimes can save you some time. So remember, impulse came from the idea that we started with F equals ma and kind of made that into something else. And we'll just kind of show you that real quickly again. Remember, if F equals ma, acceleration is equal to the change in velocity over the change in time. So you can say, all right, well, now I'm going to have F is equal to mass change in velocity over change in time. And then you can say, well, I recognize this as equal to the change in momentum. So this kind of then, if you take this delta t and put it on the other side, or multiply both sides by delta t, you end up with the force times the change in time is equal to the mass times the change in momentum. Or expanding that out a little bit, force times time is equal to mass final velocity minus mass times the initial velocity. So you can see we have a force, a time component, and velocities, which there's no acceleration in here because we kind of took care of that by expanding acceleration into something else. So going to our example problem here, we have a 15-gram arrow that is shot toward the target. It has a speed of 90 meters per second, and the arrow is stopped by the target in 0.01 seconds. What is the force produced by the target? So here's where you have to look at a couple different things. 15 grams. My mass is 15 grams, but we need to put that into something else. Remember, you move it 3 places to the left to get to kilograms. So 0.015 kilograms is the mass of my arrow. And here we have 90 meters per second. That's a usable number, so we don't have to worry about converting those things. So question is, what is the force produced? And again, a lot of times people go to F equals ma and they have to calculate the acceleration, which again will get you there. But here in one step, we can say, all right, well, force change in time is equal to mass times final velocity minus mass times the initial velocity. I guess IB way of writing this, let me do that real quick. F delta t, and you should know both, is equal to mv minus mu. As I fill this number in now, I'm looking for force. My time, 0.01 seconds, is equal to 0.015 kilograms times my final velocity, which would be 0, minus 0.015 kilograms times my initial velocity of 90 meters per second. So I start to figure this stuff out. I'm going to get 0.01 times F. If I drop my units off for just a second, is equal to 1.35 I left the units off in there, so I'll do it here too. So sorry about that. When I take 1.35, which is a pretty small number, divided by 0.01, my force, and this should be negative, sorry, is going to be equal to negative 135 newtons. And again, the negative should make sense because this is something working against that arrow's motion. It's going to be a force going that way by the target to stop that arrow because it's taking its velocity and reducing it down to 0. Okay. Another simple example of this is a 1,500 kilogram car traveling 24 meters per second, then applies their brakes and stops in 3 seconds. What is the force provided by the car's brakes to stop it? So, simply drawing a picture to kind of make this a little easier to organize my data. Here's my cheap convertible car, whatever, but they're moving this way with some velocity. The velocity is equal to 24 meters per second. Eventually, this car is going to stop and have a velocity of 0, and the time it takes for that to happen is 3.0 seconds. So what is the force provided by those brakes? Again, if we kind of remember in the previous slide, force times change in time is equal to mass times final velocity minus mass times the initial velocity. Or again, if I do it in IB notation, MV minus MU. And make sure you're careful where you put your numbers. Force is what we're looking for. My time is 3 seconds. It's equal to the mass, which is 1,500 kilograms. Again, times my final velocity, which is going to be 0 meters per second, minus 1,500 kilograms again. A little strange zero, but I guess it's still 0, times 24 meters per second. Again, I'm going to have a negative force. You can see this is basically going to cancel off. So I end up with 3 times F is equal to negative 36,000, kilogram meters per second. My force is going to be a negative 12,000 newtons. So again, when you use things like time and force together, don't forget about your impulse formula, because a lot of times it can save you time and steps when you're doing calculations.